So welcome back after the lunch break. Before we start the session, I just have to tell that if you would like to come for a lab tour to IST Austria, it would be nice if you can sign up or register by the next coffee break, because it's outside of Vienna. You have to pay for the transport, but we would like to give free pass by each name. So I need the names by to the evening. So yeah, so we will start our third lecture session by Dmitry again.
Thank you. So now I have a real challenge, ladies and gentlemen. You had lunch and now we have an hour and 15 minutes and I may have to make sure you don't fall asleep. I'll do my best. We'll see how I succeed. And what is happening here? Doesn't advance for some reason. Okay, good. All right. So we're going to continue for just a few minutes with this basic framework that we are discussing of assuming that dark matter is just one type of particle. And as I already said, so we have this 0.4 GeV per cubic centimeter that comes from observation, and then the number density of particles is just that divided by the mass of a particle. And just maybe some numbers to give you some ideas for some feeling for what we're talking about. So we really don't know what the mass is. There's a very broad range of possibilities, but if we assume, for instance, as a benchmark value that the mass is 4 times 10 to minus 9 electron volt, then if you divide these two numbers, you get that you have about 10 to the 17 of such particles per cubic centimeter, for instance. Then, so we already talked about the coherence time, and we derived it from this, that you have oscillation of the field at the Compton frequency, and this is the rest energy, and this is the kinetic energy. And if you have an ensemble, we usually assume that this is what's called virialized ensemble, that there is some kind of a thermal like distribution. Yes, so then we have this coherence time. This is the 1 over Compton time and times 10 to the 6. And for our benchmark value, this would give you coherence time of about 1 second. And the coherence length is just given by the coherence time multiplied by the velocity, which is 10 to minus 3 c or so. And so from this, we derive the coherence length for this benchmark value is about 300 kilometers. And we realized, thinking about this, that this dark matter field is sort of like laser speckle. So if you look carefully, for instance, at the structure of this spot, or if you scatter coherent light, then you see that there are places, regions where different scattered beams add sort of constructively and then destructively. So you have like bright and dark alternating pattern. And so we think that dark matter should be also like this. If you, so the size of this spot is about the coherence length, and this is not a static picture, it's living. Okay, it's changed. What was a dark spot may become bright after about the coherence time, and vice versa. So you would see it kind of twinkling. So this is really not a big problem for experiments that run much longer than the coherence time, because like if you have a long experiment, during that time everything settles, yeah, averages, and there is not a problem. But you will see that we realize there's potentially a problem if you start going to very slow oscillation frequencies and correspondingly very long coherence time. By the way, maybe I should stop here for a commercial break, and because this is a non-commercial operation, I'm going to put all commercials in one place. Okay, so the first commercial is we are always looking for talented people to join our group, be that graduate students or postdocs. We do not always have money in the bank to pay postdocs, but what happens if there's say somebody who wants to work with us and we want to work with this person, then we sometimes try to find some program, European program or German program to sort of write a joint application and things like this. So if you are still interested in exploring our group after my presentations here, then write to me an email. So that's number one commercial break. Commercial. Number two commercial. There is yeah. So at Berkeley we had this pretty grueling system of exams. So every PhD student in the course of the first year had to do 2 written exams, 4 hours long each, one in classical physics, one in quantum physics, and then pretty long oral exams. And usually the committee would consist of 2 professors, and at Berkeley, especially in the past, there were a lot of Nobel Prize winners, and I was a young assistant professor, and I was sometimes paired with people like Charlie Towns, who invented the laser, or Irving Hahn, who invented spin echoes, and actually everything else in the NMR. And I was an enormous learning experience for me, and I was very impressed. And so I wrote the questions they asked in a little notebook. And many years later, now together with my PhD student, now a professor at Boston University, Alex Sushko, we kind of collected them, plus all kinds of questions that could have been asked at Berkeley exams. And this is now physics on your feet, and the second edition of this is it's currently being printed, so it will be available very shortly. And there are some kind of short questions that can be asked at the exam. So this actually is I always tell my students, when you give lectures, never copy pages from books and articles. You should really make the slides, not because it's terrible, when there's lots of equations. But here I'm breaking my own rule and copying the page. But there are 2 reasons for this. One reason is, first, it was my book, so I and the second reason is I just want to illustrate that a lot of these things are really not so sophisticated. This is one of the messages I want to carry, that you can get pretty far with 6th grade education in this field. Yeah. Anyway, continuing this story here, and again, okay, good. All right. I don't have that. I guess here on the slide. I thought I had it, but let me just tell you. So it's not a problem for short coherence time, but I told you on the previous slide that the possible range goes down to 10 to minus 22 electron volt, and that corresponds to an oscillation frequency of 1 divided by a year, and the coherence time then is 1,000,000 times that. It's 1,000,000 years. Okay. So we're doing these experiments, and one day I went to sleep in a good mood, and then I wake up in the middle of the night because I have this scenario in my head, that we do our experiment and report that there is no dark matter, but maybe we just happen to be in one of these dark spots. And if we continue doing an experiment for a million years, okay, then we will see that there is, in fact, there is dark matter, but we were just very unlucky. And that simple idea, okay, that actually turned out a couple of two things about it. First of all, it turned out that if you really dig in the literature, you could find some theoretical papers where, if you analyze what the formulae are saying, that is there. So it's not, I mean, it's not a very sophisticated idea. And second thing I discovered, that people in this field were really resistant to admitting that there is this problem, and you have to actually modify your statistical analysis to take this horror scenario into account. And I had a hard time convincing them, and so then I had to actually write a short story about doing an experiment and discovering no dark matter, and then turning out that you're sitting in this dark spot. Now I think everybody. So the latest thing is we got submitted the paper, and we got for a review back, and we were criticized for not including this correction, actually. So I was like, okay, the community now, and there was a reason we didn't include. Anyway, okay. So how do you search for it? And on this slide, I guess I give you a very broad overview. So already we discussed NMR searches, and what I described is zero field NMR search for this axion-like particles. But in fact, sort of our flagship experiment, CASPER, cosmic axion spin precession experiment, is a high field NMR experiment. And we have actually two versions of this. It's and one is at Boston University in the laboratory of Alex Sushkov, and another one is at Mainz. But these things actually look like, in fact, high field NMR experiments. I'll show you more details after this overview. Following, so the main idea here is that dark matter field acts as effectively as an oscillating magnetic field that, when resonant with the Larmor frequency, will start flipping the spins. And this idea can also be applied to devices that are just maybe similar to NMR, but somewhat different. For instance, in Hefei, in the group of Jiangmin, we have a maser operating and looking for dark matter, and also a device that's called spin amplifier that's shown here. But the ideas are quite similar. Now, I want to say that NMR experiment is, so maybe I'll write you a little classification of dark matter experiments. And so the one big division is sort of direct search, and then indirect. So, for instance, our CASPER experiment that I described is in this column, and that is because the experiment is actually trying to measure the galactic dark matter directly. And the terminology that people have is because I told you that from the rotation curve you can kind of work out what is the distribution of dark matter in the galaxies, and it's like it should have a radius larger, so to say, than the normal matter in the galaxy. And so people talk about galactic halos, and the devices that are looking for it are called haloscopes. So our device is a haloscope, measuring directly. Now there are some other experiments because the dark matter actually dark matter particles can be produced in the sun. Maybe I'll show you how you do that. And so such experiments are called helioscopes, because dark matter is produced in the sun. That's what this means, helioscope. And then there are experiments where you do not rely on the presence of dark matter or its production in the sun. You make it yourself. And I don't know how to call this category, but I'll give you an example. And it's a very strange kind of experiments. It's called LSW. It's light shining through walls. And the way this works is one of the possible interactions, let's say an axion or axion-like particle can have. It can either decay into photons, and this is a very slow process. It happens, so the decay time is much longer than the lifetime of the universe, but it's possible. Or it can collide with a photon and produce another photon, and this photon it collides with could be very low frequency, then it's a static field. And so these experiments, they look like this. You take a laser light and you send this through a magnet. And in this magnet, some of the photons are converted to the axion. So that if you know the Feynman diagrams, so you have this axion going, and then there is this static photon from the static magnetic field, and then no, sorry, you have the laser photon, and then this makes an axion. And so here you have some of the, well, most of the photons plus some axions, presumably. Then what you do is you put a wall. And if I take, we can do this experiment now. So I take my laser, I shine it through the wall. Nothing comes out on the other side, right? Because laser photons don't go through walls. But axions, they don't care. They just go through the wall. So all you need to do is detect your axion on the other side. But there's a problem, because the axion doesn't care about the wall. It also doesn't care about your detector. It goes straight through. So people do, it's totally nuts, actually. And the most fantastic thing that it works like a charm. That's the fantastic. So what people do is they actually put now another magnet here. And so in this magnet, you can have an inverse process going on. The axion comes in, interacts with the static field, and then the photon comes in. So you convert this axion to the photon, and now you have your detector here. So that's why this is called light shining through the walls. Okay, so it turns out that you need to do this in an incredibly sophisticated way. First of all, in order to enhance this, you have to put an optical cavity here. And if you think about it, then you also need an optical cavity here. And then somehow this cavity should be exactly matched in frequency to this other cavity on the other side of the wall. And people do this. This is a very high order process. The probability here goes like there's some kind of a small interaction constant here. The probability is square of that. And here's another square, is force power of tiny number. So it shouldn't work. But the technology is so developed and people are so clever and bring it to such degrees of perfection by optimizing everything. So for instance, you gain with the figure of merit is the magnetic field times the length, and then squared. So you take big accelerator magnets, as big as you can with highest field as possible, and you make the cavity as good as possible. Same on the other side. And in the end, this is one of the most sensitive experiments that searches for the axion. So, but here it's you can call it a do-it-yourself experiment, because you make your axion, then you detect it. Okay, you do everything by yourself, and then if you find it, you can figure out eventually what the mass is and say, okay, this is a good candidate for dark matter. And we kind of indirect. Maybe I should put it. Yeah, I don't know. Maybe it should be in this category, but you understand how this works, okay? Now you can say, oh, this is such a complex experiment. I'd like to subcontract part of it to somebody else. So these helioscopes is where this production part you subcontract to the sun. There is a magnetic field. There is a lot of light. Okay, let the sun produce them. I only detect them. And in these helioscopes, we don't rely on any of this. We just get the ones we can get. There is another cool, yes. Yeah, so we need, in fact, you add, it is a very fast enhancement, because you add amplitudes and not probabilities. So it's coherent enhancement here and then coherent enhancement here. That's unfortunately not possible, but it turns out that even for photons works, because it's again for the same reason that you have on one pass some amplitude. On the second, yeah. It's also cavity for photons, and it turns out, and maybe it will take us quite a bit of time to really convince ourselves, but it turns out that it's kind of symmetric, and this cavity also helps in the same way as that cavity helps. Yeah. But so in all of this, maybe this is okay to have this all like direct searches, because here we're dealing with real axions, let's say. But in direct searches, is this idea that if I have, for instance, a real particle like electron or positron, then I can have also virtual particles. So in vacuum, I can produce an electron-positron pair. Then it goes back to a photon, and it changes, for example, electromagnetic interactions and gives anomalous G factors and whatnot. So the idea for indirect searches is that if I measure precisely interaction between, say, one spin and another spin, or spin and a mass, or something like this, I can look for something that's called Fieff's force. And so I'm still hunting for these exotic particles, but I don't need to produce them as real particles that can be virtual. And so actually, it's an interesting area. And even if we are not looking for dark matter, but just looking for possible other exotic physics, you may find some particles that exist but are not part of dark matter. And so it turns out that you can easily convert your helioscope into a device to look for this type of interaction. So in Hefei, we have this a device that resembles a helicopter. It's about this big, and there is a mass that's rotating near a magnetic shield, and there is the magnetometer over there. It's actually the same device as in the previous picture, and it's looking for synchronous modulation, and this is the kind of indirect search. Then we have a search for another interesting possibility. So in the simplest case, we just kind of have this field, and it's more or less, apart from the fluctuations, it's more or less uniform apart from the stochasticity. But there are other models in which dark matter assumes some shapes, and this is called topological dark matter. And one of the possibilities is that you have so-called domain walls, where it's a region in space where you have a large gradient of this axion-like field, if you like, and sort of the surface tension, if you like, of this axion field is the energy of the dark matter, is the dark matter itself. And then once in a while, these things exist. Once in a while, the Earth will collide with such objects, and then because there is a quasi-magnetic field associated with this gradient of the axion field, we can have a network of magnetometers all around the planet, and as we fly through this wall, these magnetometers will fire a sort of the signal in a particular pattern. Actually, many years ago, when we submitted a paper to Physical Review Letter proposing this, we called this paper "How do you know that you went through the wall?" or something like this, some playful title. And this was accepted. It was fine, and then we were very happy. And then the paper comes out, and the title is something crazy that is not even correct in English. It's like a search for walls of the axion models or something. Something that's not right, even in, grammatically. And it turns out in the last minute, the editors looked at the title. How do you know that you went through the wall? I said, no, it's not. Yeah, it was not. Okay, I'll show you actually a movie how this works. Then this is something interesting and possibly related to what Philippe Bouillet was talking about. So if you assume that dark matter interacts weakly with normal matter, say you have some object made of this, and this is a bit suggestively drawn there, you see, then this kind of object can go through the Earth. And if it is, it has to interact gravitationally. And if it somehow gets trapped by the Earth field, it could, for example, slosh around or go on some trajectory inside the Earth. And because this object is massive, maybe you can detect it with gravimeters, and that's something that we've done. It turns out that there are the superconducting gravimeters that geophysicists have installed around the Earth. They've been in operation for the last 40 years or so. They are incredibly sensitive. So Philippe was talking about 10 to minus 9 Gs. One of these devices is 10 to minus 11, 10 to minus 12 Gs per root hertz, exceptionally sensitive. And they feed the data, and you can get it online. And so you can then look at the data and try to find some patterns. So we did this, as it was quite a bit of fun. And then you have to think how this kind of thing can relate to dark matter and whether it can be or not. And there are many questions. So if these guys do not interact, how do they get trapped? And it's a big problem with many scenarios. But there are answers, some kind of answers to everything. All right. Now, I mostly talked about axions, and the way they interact is through their effect on spins. So that's why we do NMR experiment. But remember, I said that there is also a possibility that dark matter is a scalar particle, and scalar particles do not interact with spins. But if you look at the Lagrangian, possible Lagrangian of their interaction, you notice something interesting, that the effect of such a field could be effectively described as a change in fundamental constants. So, for example, the mass of an electron or a mass of a proton, or alpha, the fine structure constant. Now, for a while, it was recognized that this is a nice way to look for very slow changes of fundamental constants, and so clock people have been looking, including ourselves, at this for a while. But recently, attention was drawn to fast oscillating particles, maybe hundreds of megahertz or something. And the question was, how do you search for this when atomic clocks update very infrequently? So maybe some clocks update once a minute, the very fast clocks update once a second. But how do you look for something that's 100 megahertz? And then we proposed something that seemed a bit crazy at first. So we were a bit worried sending it for publication. And the idea is that so you have an energy of an atomic state, and it depends on fundamental constants, for instance, alpha. And if the fundamental constants are changing, this energy has to be vibrating like this. And then if you have for example, an optical cavity, then its length also depends on the constants, but in another way. And so if you take your laser, for instance, and lock to the cavity, and now try to look at the transition at the frequency of an atomic transition, you might see such an oscillation. And we put this together. This looks complicated, but in fact, this is saturation spectroscopy, Doppler-free saturation spectroscopy thing that you find in undergraduate labs. And also, if you have optical lasers, you have these little modules, commercial, that has this built-in, if you like, not exactly what we did, but so it's actually something really, really common. And so we set up such an experiment, and it turns out that, you know, in a few days you can reach delta nu over nu of 10 to minus 16, or better, now we are at 10 to the minus 18. And so we wrote it up. So we were really worried that it's so simple that we made some mistake. There are two worries: either we made some mistake in our logic, or people have done it already. We couldn't find that people have done it already. Mistake, you know, we looked for it, so we sent it. It was published. Now everybody's doing it. This? Yeah, it's cesium vapor cell, and then here we do it's a bit fancy in this case. It's called the polarization spectroscopy. It's a modulation-free, Doppler-free technique that allows you that has, you know, linear dispersion. So if atomic frequency is changing, you get a sort of a proportional change in the signal. Yeah, but so this is like 3 orders of magnitude simpler than your thesis experiment, I would say. Okay. Another interesting way to look for dark matter. So we have some friends who are members of the BASE collaboration based at CERN. And what these guys do is that they catch antiprotons, the antiparticles of a proton, and they put them in fancy traps. Here actually is a trap that has 2 of them, and they keep them for months. So the technique is so amazing that their lifetime is very, very long. For months they live there, and what they do is they measure magnetic moment of antiproton, and then there is a copy of this experiment at Mainz that works with protons. Actually, now the guys are working on making a portable trap. So you go to CERN, you load your trap with antiprotons, you bring it to Mainz, and then you can do both of them in the same trap. So the idea was again to look for possible effect of dark matter on these antiproton spins. And if you assume that the effect of dark matter on antimatter is the same as its effect on normal matter, this is not a super sensitive experiment. It's okay, but it's not like fantastically sensitive. But the special thing is that now you use antimatter as a probe for dark matter. And there are scenarios, they are not trivial scenarios, but there are scenarios that your dark matter would interact completely differently with antimatter. Could also be possibly a solution for the matter-antimatter problem. And in this case, having this antimatter probe for dark matter is very important. And this what this experiment accomplished. So this is very exciting. So all of these experiments have been done and published already. And then I show here a new, relatively new idea. Maybe I'll have time to tell you, maybe not. It's about using levitated magnets as sensors for magnetic fields or for exotic fields. And we think that this could be actually very promising for certain kinds of experiment, levitated magnets. All right. So now let me show you, while you're still awake, a movie about how this works. This was, I don't want to say this was the very first network search for exotic physics. That would be a lie, because for instance, LIGO experiment that detected gravitational waves is already a network consisting of two different detectors, and now there are more. But maybe in the context of the dark matter, this was the first one, and so our idea was to use magnetometers, and later on people picked this up and established networks of clocks, and now there is a good reason to actually unite all these networks and have sort of universal sensor networks, because now there are theoretical reasons to do this. Initially, theories were, beating, themselves on the chest and saying, no, it's either clocks or magnetometers, because one is scalar, you don't understand that one is scalar, it doesn't interact with spin, and another is pseudoscalar, it interacts with the spin, no reason to compare them. Of course, a few years later, there are these models of particles that have both scalar and pseudoscalar interactions, and now it's extremely well motivated to mix up your networks. It's been operating for a long time. Sorry, I should probably update this, but this was our GNOME global network of optical magnetometers for exotic physics searches meeting at Mainz. This was in 2019. It's usually an annual meeting, but we didn't meet because of the COVID. And actually, if you go to our webpage, you can see in real time the map of the world with all these different stations, and you can see from this that I'm an honest person, because I showed you when it's red, it means that it's not streaming data. So I didn't choose a particularly favorable time to do this. I think now you will see most of them green, because now we're in the middle of the data run. Yeah, but it's looking for these domain walls. And one thing that I want to say is we learned the hard way, is that doing an experiment sometimes is the easiest thing, and when this experiment involves sophisticated data analysis, that could really be a bottleneck. And so I'm now showing you what was happening in 2016 17, and we're just now publishing the results. I'm ashamed of this. I'm not proud of this. This is a result of making some wrong decisions in the beginning. For instance, we decided to rely on the public software by LIGO in our experiment, and that was a big mistake. We ended up wasting a few years doing that. So there's data science is serious science, which you need to know. Anyway, here is the object that you, oops. That would be bad if it doesn't run, but let's see. Yeah, yes, it runs. Okay, so this is the Earth, and these are our stations. You find one in Krakow. That's actually Berkeley and Krakow were the first ones in this network. So in each of these locations, there is a fairly sensitive atomic magnetometer in a multi-layer magnetic shield. And the way we operate the magnetometers, they actually have a sensitive direction. And I think now we will have these arrows showing the sensitive directions appearing over there. So this is the direction of the average velocity of the Earth in the galaxy. So there is we don't know which direction this domain wall will come from, but it's more likely, a bit more likely, that it will come from the direction opposite to the direction of the Earth's motion. So these are the sensitive direction for the magnetic field for each of the stations. And now I think we'll have this wall. So we go through it, and as we go, that's the idea, that there is a particular pattern of the signals that we should be able to see. And from the relative timing and relative size of the signal, we can reconstruct where the wall was going from, what its speed was, and what the strength of interaction is. And yeah, we're kind of excited about this. It gives interesting results. So far, we haven't found dark matter. You would have heard much more loud speech here if you have. But as we are doing this experiment, we are discovering that new ideas for what this kind of search can look for pop up all the time. And for instance, recently, we are not only looking for galactic dark matter, but also for exotic particles that may have originated in catastrophic events in the universe, like black hole mergers, and so on. Okay, time out. Yeah, sorry. We are not sure. We look for it. We look for it. It should be very large. It should be comparable maybe to the galactic scale or something, according to these 3D models. But the science case is expanding, and we need to stop now. But just one thing I wanted to say, that we realized at some point that if you are doing any kind of precision experiment, okay, any kind of precision experiment, it's highly recommended that you take a GPS timing reference and you basically store your data with a timestamp and as much information as possible, because I have written more than half a dozen PRLs based on data taken years before that for completely different reasons. And then you have an idea, and then you can do this couch experiment, basically, go back, dig up your data, analyze it. You're looking for slow variation of constants. Now you go back and you look for that just at that level. So highly recommended. Storage is cheap, so store your data and timestamp it. And we continue after coffee.
You still have half an hour.
Oh, good. Ah, you guys are incredibly well organized, I must say. Actually, the whole school is organized fantastically. So, um, you hope, okay? You hope. Yes. So this is about the detection method. Some details for you in the Physics of the Dark Universe journal, you know, and now this is about to, I think, we have all the indication that this will be accepted in Nature Physics, and because it went through all the reviews, so should appear there very shortly. I want to mention, because there is a lot of talk about nitrogen vacancy centers here, that you can also use nitrogen, nitrogen vacancy centers to look for fused forces. That is going to be these indirect searches. And this is very nice. Remember, what is the advantage of nitrogen vacancy center? That it allows you to measure things on a microscopic scale, eventually down to atomic scale. And so there is a group at USTC, again, and it's a young fellow, young professor by the name Jing Rong is leading this, and this is part of a larger group of Zhenfeng Du, who Anjusha probably knows from publications. They have been for several years looking for different kinds of exotic interactions. So there are, you know, like I said, spin-spin interactions, spin-mass interactions, dependent on velocities, not dependent. And so they were happily publishing every year or two new limits on some kind of forces, which is very important. And then last year, they have discovered something which is very interesting and exciting. I think it's a bit too early to celebrate the discovery of the new particle, but they have some evidence, and they now have to figure out where it's coming from. So it's very exciting. Maybe it is new particle, but I think it's a bit too early. So it's on the archive if you like. So now these exotic interactions, they can be classified, and so you can say, well, let's assume that I have a new pseudoscalar particle, for example, of a certain mass. What kind of fifth forces can it produce? And there were several catalogs done in the past, starting by the one by Frank Wilczek. That's the guy who thought of the name Axion, and his colleagues, and then it was revised. And it turns out that there were slight problems with all the catalogs. They were either incomplete or had some errors. And so this catalog was recently sort of revisited and rewritten in different ways. And so these two PhD students, Pavel Fadeev is a PhD student in our group, and this is Philip Ficek. He is a student, almost I think a PhD now, at the Jagiellonian University, and he came a few years back when he was an undergraduate student. He came for a summer internship with us, and we got a strong hold of him and wouldn't let him go till now. These are amazing guys, and this is now the latest catalog. And yes, these are the successive publications from the Jing Rong group. So you can see here the range of the interaction. So they explore basically from micron to hundreds of microns, and have improved on a lot of this potential. So see, they typically have spins of particles, and sometimes they have velocities of particles. So those were their previous publications, and then the one that actually, don't trust me on this. I thought it was resolved, but I think it's not. It's still, they're still seeing something. So that's in this paper. So they're seeing some evidence for something interesting. All right. So I'll quickly tell you a story now about these precessing ferromagnetic magnetometers, and this starts with a exam question, right? Which is a problem in our book on atomic physics, and the question is this. Let's see. Let's do the exam now. Why not? So so if you take an atomic spin, for example, and you prepare it at an angle to a magnetic field, and you let the spin go, what happens? Yeah, it precesses. Good. You passed the first part. Excellent. Second part. Instead of the spin, we take a magnetic needle, compass needle, for example, and we also prepare it at an angle to a magnetic field and let it go. What will it do? Yeah, I see some gestures. Yeah, so it wants to, instead of precession, it will go align with the north, and then because it has inertia, it will miss. So it will be oscillating like this, and eventually will come to rest after dissipation towards the north. And the question is, good. So you passed the second part too. Now comes the third part. Why is it such a different behavior? What's different between a magnetic needle and an atomic spin? What? Size? Well, you might say, which friction? I'd say it's a needle with no gravity and vacuum, so there's no friction. Well, yes. Sorry. No, it's magnetized. So a needle is basically a magnet that has the shape like this. So it has north, south. Yeah, so it's magnetized in that direction. And in fact, if you look up in Kittel or something, you will find that so if you have n atoms, let's say iron or something like this, right, or cobalt, and then there is on the order of h bar of angular momentum from atoms. So it's if you say that the angular momentum is different, so in one atom it's h bar per atom, and here it's h bar per atom. So that's not the difference. Domains. Yeah, so it's true that the spins are locked, and that's very important. Okay, let me tell you. The difference is that if you take this mechanical object, right, then there is this classical orbital momentum. In fact, you have to be careful because this is a tensor relation in general. And when you talk about the needle, when it starts to move, then this orbital, this momentum of so basically big body that dominates, and so now you can forget about the spins. But if you go, so there is this, and then there is this angular momentum, and atoms times h bar. So if you go to a small magnetic field which doesn't try to move this thing very rapidly, we can be in the regime where, in fact, this term dominates, the intrinsic atomic angular momentum. And the prediction is that in that case, the needle should be undergoing precession with the same Larmor frequency as an atom. So there are two regimes. In very small magnetic field, it should be precessing. In higher magnetic field, it should do this. And the fields that you need are small, but not crazy. So if you're talking about particle, maybe 10 micron long or something like this, it's a field that you can easily achieve in this multi-layer shielding. Okay, so that's a problem that we put in this book. This is Alex Sushkov. This is Derek Kimball, and this is the book we wrote now with Derek, not with Alex. It's an early one. Okay, but then some years later, we just had this thought. Why don't we have a look at the sensitivity of a magnetometer based on the precession of a needle? You know, just out of fun. So you take a needle, you make it so that it can freely rotate, and then you measure the direction, for instance, putting a squid magnetometer that can measure the magnetic flux. Let's estimate the sensitivity. We started doing this, and we couldn't believe our eyes what the results were. We were getting amazing sensitivity, like incomparably better than you would get from an ensemble of independent atoms. There's, I mean, there are details. So there's, for example, this is a sensitivity of due to a standard quantum limit, and we were getting much better scalings and much better sensitivities, and we were thinking that we are making a mistake somewhere, but then we actually realized what the reason for this is, and now we think that these kind of solid state sensors are actually some of the best sensors that you can make. They're very difficult to realize for a strange reason that it's hard to make a suspension, because even if you hang it on a nanotube, the forces are overwhelming. So in the end, we will probably need to drop them and have them being in free fall, but they are incredibly sensitive, and so we hope to use them. Maybe I show it here. So we hope to use them for searches for exotic forces, and this is described here. But this is for exotic forces. But also we would like to have this what we call gravity probe spin. Use them to test the effect of gravity on quantum spins. So people always talk about connection between gravity and quantum mechanics. So we would like to ask very, very simple question. Does the gravity affect gyro, you know, the mechanical gyro and spin in the same way? So no sophisticated theory, which is this very question. And I think it should work. So you heard already about this gravity probe B experiment that launched the rotating gyros and detected the general relativity effects. There are two. There is this frame dragging effect or lens steering effect, and also a de Sitter effect. And gravity probe B showed that general relativity works for classical objects. So here, with our estimates show that such a ferromagnetic device can also allow to test this for spins. Right, and I think maybe this is a good place to take a break and go for poster session. Coffee. Thank you. Thank you.
So in
I'm super sorry. The masks make it hard to understand. Yes, yes. Where is that reference? On the previous slide. We have done it, and other people have done it. It's not. It's fun to do, but it's not clean enough for these experiments. I'm not quite optimistic. Yeah, that paper. That's from an experiment we've done at Berkeley. That's what are the issues? Imperfections of your superconductor, frozen fluxes, and so on. So it's very interesting, but it's very dirty, and I would say not usable for precision experiments. There are people who have done significantly better than us. Henrik Ulbricht at Southampton, I think, has the best kind of device for this. But I think eventually we would have to basically have them in free fall. And before we go to space, we would like to go to this amazing facility called Einstein Elevator, which is in Hanover. So that's our dream now to do that. I can tell you, now we have to drink coffee, but I can tell you how this Einstein Elevator works. It's amazing.
question? No? Okay.
So before some of you be surprised that your posters are not out there, I had to rearrange them a bit because there will be a catering coming. So moved some of them to where the registration desk is. So if you couldn't find your poster, let me know. Yes, so the weather is good still, so it's better to have your coffee outside when you remove your mask. And we have also the normal surgical masks if you don't feel okay with FFP2 masks. And yeah, the beer we will have after the special lecture. Of course, we thought it's not a good idea to have the beer with poster session before Roman's lecture. So so yes. So now the winners of the pop quiz. Who was it? Sebastian, you were one of them. Who was else? Yeah. Please. Ria, where is the prize?
Yep. Would you like to come down to get your prize, please? You will see, wait.